Hello everyone, I want to tell you today about the energy stored by a capacitor. So I also have my notebook for drawing, and I will write down the topic: energy. Energy stored by a capacitor. Energy stored by a capacitor. That's it. On the previous lesson we looked at the capacitor. Yes, that is the component of the circuits, very popular, one of the most popular, and we can say that when we have capacitance in our circuit, so capacitance can store the charge. And also we can say that as capacitor stores the charge, it also stores energy. So this energy could be used as it can be used for some other components to work in the circuit that are connected as well. So, and also we can make the definition for the energy, that the energy is the probability of making a work. So work could be done exactly because we have energy. So it also it is so not only for physics but for our everyday life. And what to start with? Yes, we started with the definition of energy, that's good, and then we continue with graphic, how we can draw the energy on plot. So we need a plot, yes, charge versus voltage. Yes, so charge usually counted in coulomb units and voltage in volts. Yes, so you can see that. And we should say that for capacitor, yes, don't remember have we already considered this point or not, but for the capacitor we have such a linear dependence. And also the we have, for example, the angle. For example, it is alpha, so the tangent of alpha will be exactly this property of capacitance. And we can see that if we will make such a line, for example, we need this amount of voltage stored by capacitor, and it means that we can collect this amount of charge, and this depends on this angle. Yes, the angle of the capacitor. And yes, that's also the definition of the capacitor using the graph. And I think we need one more time to draw our circuit that consists of direct power supply, resistor, capacitor, and ammeter. That's it. Yes, we need to repeat one more time what is going on when we put capacitor in our circuit. So direct current power supply began to charge the capacitor. It means that negative charged electrons, they go and they begin to be stored, they begin to be collected on one of the plates. Yes, here it's right plate, and here we can draw minuses. Yes, that means that we will have pluses on the other plate. Yes, because all the minuses will go and will go further. Yes, and this flowing of electrons is exactly the current flow. And what is going on the capacitor? We have these electrons, and it means that in a result we have a positive charge of the capacitor on it. And as we said that capacitor can store energy, we want also to count this energy. Yes, we are interested how to count this energy. We know that for electrostatic field we have an equation that energy is counted as charge multiplied by voltage. So that's the popular equation, and this equation works when we have for example just one electron that we needed to transfer, to transfer from direct current power supply, for example, to capacitor, or from one place to another place, if to be correct. And so it's okay, this formula works okay for the one electron. I can draw it for the one, yes. But for the capacitor it's a different situation, because when we put, for example, we want to make work, yes, put in another electron to the capacitor, the right plate, we need it also not only to make work of transferring the second electron, but we need to make work against the previous electrons that already stored on the capacitor plate. That means that we need to make this work 2 times more, 2 works more. And as more capacitors we want to put, as more charges we want to put on the capacitor, we need to make the double work. So exactly this plot explains this as well. So when we the next amount, yes, of charge we wanted to put, yes, amount of charge, more voltage is needed, yes, we can say like this. And what does it mean? It means that we will not have this equation. This equation works with the situation when we have, for example, here is Q, here is V. Yes, you can see that. And we have the constant Q. So it means that just for electrostatic field we will have the constant Q, and this area, yes, if to count this area, this will be exactly the work or the energy in our case. And this was the case just for current flow, yes, without a capacitor, just when we have only a resistance in our schema, in our circuit. And when we have a capacitor, you can see we have a different plot, but the idea is the same, to count energy of the capacitor, or it means the work done by the capacitor, yes, by the current that put electrons to the capacitor, by the field. We need to count area, and here will be such equation, QV divided by 2. That's it. So you can see that it's just the formula for triangular, because here is Q, here is Q side, here is V side, here is V, and we need to count the triangular. That's it. So that's how geometry helps us to understand formulas more. And that's very nice. And we can write down not only this formula, yes, we know this formula now for energy, yes, it means that QV divided by 2, but we also know the formula that C is Q divided by V. We can put this here and we will have more derivatives. It means that we will have such formula, CV squared divided by 2, and Q squared divided by 2C. where C is capacitance of the capacitor, Q is a charge collected or stored by the capacitor, and V is the voltage that now also a capacitor has. Yes, and that's it. So, and now we can see the example of where the capacitor is used and how its energy can be used. For example, we have a photo camera, an old photo camera, and it usually had flashlights. So now we will draw the schema for this flashlight, and we'll understand how it really works. So you remember this flashlight, it works in a very short time, in some seconds or even milliseconds, and also we can do that because we have such component as capacitor. So we will have the next circuit. Yes, here is switch 1, switch 2. Yes, here will be the capacitor, our capacitor. Here will be direct current and voltage power supply. We can call it direct current and voltage power supply. Here will be a discharging tube or lamp, discharging tube or lamp. That's it. So we can look deeper what's going on here. So first of all, we switch the first switch and the capacitor begins to charge. It will charge until it will have the same voltage as on the direct current and voltage power supply. After that, the current will not go anymore, will not flow. And we can switch off. For example, now we can say that we have charged capacitor. After that, we switched the second switch, and what will goes on? The current will flow from the capacitor. Capacitor will play the role as a direct current power supply, but for just a short time, for the time of the capacitor is recharging. And during this short period of time, the capacitor is recharging, and at that time this lamp flashes. Yes, that's it. That's how we have this flash. And this sound of flash also goes because of this capacitor discharged and lamp flash. And now we can resolve one of the tasks about this topic. So these tasks, I will try to find one of such tasks. For example, it's this one. I will read it. A capacitor can be used in a camera to provide a large amount of energy to the camera flash in a short amount of time. So exactly as I have painted for you. And also we have some parameters that were put to this schema. So we have, for example, 9 volts voltage, and we have hundreds of millifarads. Yes, for capacitance. That's it. And we need to count some parameters. So, for example, what do we need to count? Yes, I will use the cleaner page. For example, we need to calculate the maximum energy stored by the capacitor. So, we need this formula for energy. And we remember that we have capacitance and voltage, so we can use a formula with these parameters. So CV squared divided by 2. Yes, we have 210 minus 6. Here will be 9 or what? 9. 9. So 9 squared 9, 81 divided by 2. And you can see we'll have 100 here, so 8,100, then minus 6, so it is it all right or not? One moment. So I think if I have some mistakes in this, if resolving this task, if it's minus 6, so it will be 8.1 multiple 10 minus 3. Yes, it will be minus 3. That's it. Yeah. So so we can say that it's 8.1 millijoule. Yeah, for example, like this. That's it. Great. So maybe some more that we can count here. Calculate the charge stored by the capacitor. So charge, it's easy. It's just CV, we can say. So it's just 200 10 minus 6 multiple 9. Yes, it will be 1800 multiple 10 minus 6, or 1.8 millicoulomb. Yes, it's millicoulomb. That's great. The next point, for example, we have additional information about the time, how much time is needed to discharge a capacitor. So time can be 35 seconds, for example. And no, not 35, 3 milliseconds. 3 milliseconds, for example. So, and we need to count the average current for that. So we need to remember the equation for current. It's the amount of charge going through the conductor in a second, in some period of time. So we can exactly use Q that we have already known, divided by 3, 10 minus 3. And here will be 0.6 ampere. Yes, that's it. And maybe we want to find one more parameter. It can be the average power. The average power. So power is P, and usually it can be found as work divided by time, so how fast we can do the work. And also in here we can compare and say that our energy is equal to our work, for example. So energy of a capacitor can produce the work. So we can make it energy divided by time, and we already found the energy. Yes, it's 8.1 multiple 10 minus 3. Here is 10 3 multiple 10 to the power of minus 3. Yes, and here will be 2.7, and that's all. That's all. 2.7 watt. That's it. So I told you a little bit more about the energy, and how it could be stored by a capacitor, and also it can be stored not only for the flashlight, but for example if we need an additional power for the computer in the case when our official power source will be broken. So also we can use the capacitor that we store some energy, and will give it during this time of discharging the capacitor. The computer can be turned off properly, and all will be okay with your data, for example. That's it. So thank you for listening, and see you on the next electricity lecture.